Hey, and welcome to the second part of functions. So today's going to be a little less intense than last time. Hopefully it'll be a shorter video. We just got to talk about compositions of functions, which is really related to inverse functions, which are particular pairs of functions. So starting with compositions, compositions is just when we shove one function into another function. We can do this with variables, or we can do this with numbers, either way. I'm going to make myself a little space. I think I got these a little too close together. If we wanted to figure out what just, I'm going to start here, g of f of 0. We start out with this middle piece and we figure out, okay, well, what is f of 0? Well, that's 0 plus 1. So that's just 1. So now instead of f of 0, we've got 1. And then you figure out, okay, well, what's g of 1? Well, then you shove a 1 right here, and 1 minus 1, that's just 0. Gets a little more interesting when you actually take the two functions and put the whole function into the other one. So this one is looking for g of x. Well, g of x is x minus 1. Now we want to figure out, okay, well, what's f of x minus 1? So we're going to replace this x with an x minus 1. So we get x minus 1 plus 1. Why are I plus and minus? So x minus 1 plus 1, that ends up being just x. Oh, well, that's neat. You can do the same thing in reverse. You can take f of x, which is x plus 1. F of x is x plus 1, so x plus 1, that's taking the place of this. Still want to find g of this. Maleficent wants to help too. Um, Now we want to do x minus 1, where our x is an x plus 1. So we get x plus 1 minus 1. And we end up with just x again. Hey, well, that's neat. That's related to that inverse thing that's coming a little bit sooner. If you want to check out the other ones, check out the PDF notes. Maleficent is happy to help us out, aren't you? Say hello to everybody. Hi! All right, next thing, we're going to look at a little bit more interesting functions. So for these ones, going to hop to our perch maybe? Maybe yes, no, maybe so. That's okay. I mostly just need you to look at stuff right now. So I graphed f of x and g of x. So again, we're doing, this is Finney on page 18, number 53. I've graphed both of them on the same axes, so there they are. Now don't show them your butt. We've talked about this, it's rude. So we want to figure out what would happen if we put these functions into each other. Cool thing about Desmos is it'll do that for you. So here I've got g of f of x. I'm going to get rid of those other two. She's off to her perch now. And it turned out to be this straight line. Okay. What about if we do this the other way, f of g of x? Hey, that's also just a straight line. Oh, what cool things. So it's turning into just being x. So the conjecture that we're going to make, and it's going to seem a little wild, is that the two functions, their domain and ranges are swapped. Ooh, we'll find out more about that because they wanted us to make a conjecture. So domain and range is going to be swapped between those two. That's my prediction that I'm making right now. We'll see how that goes. So to confirm that, we're going to figure out the formulas of f of g and g of f. So f of g, domain and range, oh yeah, domain and range of each function is just all real numbers, all real numbers. So f of g is going to be this. We're going to take this piece and we're going to put it in these two spots, in the three x spots, the two x spots. Ugh. So we have, I'm going to write g, oh, I'm going to write g here in purple. So we got 3 times, in red we got 2x minus 1 over x plus 3 plus 1 over, and then we've got 2 minus 2x minus 1 Oh, that's wrong. And then x plus 3. And I'm just double checking, make sure I wrote everything correctly. 2 minus x, 2x minus 1, x plus 3. Okay, great. So we're all set. Now what we want to do is we want to try to simplify this whole thing. So what I'm going to do first is I'm going to multiply every term by x plus 3. That's going to get rid of some of this fraction and fraction business. So let's multiply the numerator and the denominator by x plus 3. That'll kind of clean things up a little bit for us. So we get 3 times 2x minus 1, because that red denominator goes away, plus 1 times x plus 3 is x plus 3. And the denominator, we've got 2 times x plus 3. And then minus, we've got 2x minus 1. All right. So simplifying that numerator, it looks like we've got 3 times 2x, that's 6x, plus another x, we got 7x. And then negative 3 plus 3, that's just 0, so nothing. And the denominator, we've got 2x, and then minus 2x, so that's just 0. And then we've got 6 plus 1, so that is 7. So this is just 7x and a 7, which is just x. So it seemed like the domain and range for this function is all real numbers. However, we need to look at the restrictions that are on the domain that happened at the beginning, because we need to go back to the beginning and worry about what would be really bad if in this earlier stage. Sure, here anything could happen, but we still need to worry about, hey, right here, x can't be negative 3. And I think 2 would also be bad, because if we, because if f of x ever spit out a 2, then we'd be in big trouble, because then this thing would kind of blow up. So whatever would make this be a 2? Yeah. So 2x minus 1 over x plus 3. If this ever equaled 2, we'd have a 0 in that big purple denominator, and that's no good. So we get 2x minus 1 equals 2x plus 6. And that seems to be not possible, which is good, because we wouldn't want it to be possible. You're going to subtract a 2x, and then the x's cancel out, and you get negative 1 equals 6. So fortunately, f of x never spits out a 2. You can even probably see that in our graph. We checked f of x. So here's f of x. See how it seems to be like skipping over that 2 spot, so it's never quite reaching 2, which is good, because if it ever spit out a 2, freak out for g of x. So our domain of this thing is negative infinity to negative 3, skip over negative 3, and go negative 3 to infinity. You can do the same thing for the range, just kind of flip around, but I want to try to keep these videos a little bit shorter. So if you want to see more information, you can check out the PDF notes. I'll also do G of F on there, but it's going to follow the same process. So next we're going to do that same thing. We're going to do it with a little bit simpler functions, because I only want to do one crazy one. Oh wait, no, this one I'm just going to do on the PDF notes. So if you want another example of this, some simpler functions, you should try out this one, and I'll do this in the PDF notes. We've been talking about like these things seem to be spinning each other out. They are inverse functions. When you mesh them together in a composite and they spit out just an x, that is a sign that they are an inverse function. In order to have an inverse, you first need to be a one-to-one function. What these are is it's a function that you put one thing in, you get one thing out. But to get that thing out, there's only one way to get that thing. So we use the horizontal line test. Just like the vertical line test, we passed a vertical line across our thing. That checked if it was a function. If it also passes the same kind of test, but with a horizontal line, then it is a one-to-one function and is able to have an inverse. If it doesn't pass both those tests, it cannot have an inverse. So here's a couple functions, and we're curious, hey, are these one-to-one functions? And these are both one-to-one functions. Well, actually, only one of them is, I should say. So I grab my horizontal line here. Whoop. Reciprocal is a tricky one. It seems like it's not going to be a one-to-one function. Like you're a little worried right here, but it actually doesn't exist at that point. It gets very, very close to 0, but there's no way that this value is ever going to be 0. It will be very close to it, but it will never quite reach it. So this one is a one-to-one. So this one is yes. This other one, however, is not, because it is a good function if you pass, if you pass a vertical line across it, it will only ever touch it once. However, it does fail our horizontal line test. So there are 2 ways for this function to spit out, what is that, 0.25? No, 0.5. So there's 2 ways that this function will spit out 0.5. One with -1 and another with +1. So there's 2 ways to get that. So this is not a one-to-one function. Since it's not one-to-one, that thing has no inverse. This one does have an inverse. So you can check to see if 2 functions are inverses, see if they're reflected across the line y equals 1. That was actually back on Desmos, the graph that we were making when it was just this straight line. So we're checking if it's reflected across that. We can see that with these 2, where they're reflected across this green line, making them inverses. You can also check if their tables are swapped, because what you're really doing is taking your x and y values and flipping them around. If their tables are swapped, then they're inverses of each other. You can also do the compositions in both directions. If it works in both directions, then it is an inverse function. To find it, you swap x and y, which is an illegal math move, but it's how you create an inverse, because you're making a new function that's the inverse of the original. You solve for y, and then this is our notation for inverses. It's f to the -1. So if you see that, it's referring to an inverse. So we want to show that f and g are inverse functions, and we're going to do it in a few ways. We're going to do it analytically, we're going to do it numerically, and we're going to do it graphically. Analytically is when we're going to plug them into each other and make sure that they spit out x. Numerically, we're going to put in a number and see it spits out the same way both ways. And then graphically, we're just going to put a graph of them and just make sure that they're reflected across the proper line. So let's start with A, analytically. We're going to do another one of those compositions of functions. So I'm going to start with f of g of x. So I'm going to put g into f. So that is, if I draw f, that is 1 plus, 1 over 1 plus. And then we want to put g of x in that x spot for x. So this little thing right there, we want to put g of x right there. So that's 1 minus x over x. To simplify this thing, I'm going to multiply top and bottom by x again. So we get x over 1 times x is x, plus that little fraction gets canceled out when it's multiplied by x, 1 minus x. In the denominator, that two x's, they cancel each other out, so we get x over 1, which is just x. So sweet. Now we got to check it the other way because it's got to work both ways. We're going to do g of f of x. So we're going to do g in green. So we've got 1 minus, we're going to have to put a thing there, over somebody else. And that thing that we're going to have to put there is f of x, which is 1 plus x, 1 over 1 plus x. And then we'll put that same thing in the denominator, 1 over 1 plus x. We're going to do the same sort of solving step. We're going to multiply top and bottom by 1 plus x, which multiplies each one of those terms. So this 1 right there being multiplied by 1 plus x gets us 1 plus x, minus, we've got to do this thing being multiplied by 1 plus x, which just kind of cancels out with itself. So we end up with just a 1. Same thing in the denominator. When this is multiplied by 1 plus x, we're left with just a 1. So we end up with 1 minus 1, that's 0, x over 1. Since those both ended up equaling just x, those two are inverses of each other. We have shown that analytically. If we wanted to show it numerically, we would pick a number and see what happens when we put it into each function. If we, we'll try that out. Let's do 3. That's what I'm going to use. So I want to figure out what f of 3 is. So that's 1 over 1 plus 3, which is a quarter. Okay, great. Now, if it's an inverse, I should be able to do g of a quarter, and this should equal 3. So I get 1 minus a quarter over a quarter. So that's 3 quarters. And I'm going to multiply by reciprocal, because dividing by a quarter is the same as multiplying by, keep flip change. That was a terrible sentence. So 3 quarters times 4 over 1. Hey, that's 3. Sweet. So since I was able to put in 3 and I got 1/4, and we did 1/4 and we got out 3, that's doing that numerical check. Our last one is we want to graphically check to see if these two things are inverses. So let me get a fresh Desmos going. So we'll say f of x equals 1 divided by 1 plus x. So there's f of x. And then for our g of x equals 1 minus x divided by x. Now this one's going to be a little trickier to see. And just for fun, I'm also going to graph the line y equals x, so we can kind of see that they're being reflected. See how this point right here is hopping over and going to that point. See how this one right here is kind of hopping over and going to that one. This point where it's going through the line y equals x is just going nowhere. So it is doing that nice reflection across that line. It's kind of tough to see with these rational functions, but it is doing it. Just kind of pick particular points and look for those to be flipped. All right. So do a little matching. So this is where you can see it a little bit better if we kind of play a little matching. And this one is actually wrong in the textbook. So in the Larson book, it's got this graph 2 times. This is the correct graph. You can see it a lot better with this root function and its inverse. See how these two are somewhat reflected across that line, where one of them's curving this way and the other one's curving up. So they do meet at a certain point together, but they're curving with each other. This is a cube root and a cubic, and see how well they match up with each other when they're reflected. This thing flips into just the lower right-hand part of the quadrant instead of the upper left-hand part. This was the lower right-hand part, and now it becomes the upper left-hand part. If we had this one, these two flip very, very, very nicely because it's just, here's our line through the middle and it hops right over. Take a look at these two. They're just kind of like a rotation almost, is it's what it kind of seems like, but also kind of rotate and flip sort of thing. So these would be all of our pairings, functions and whatnot, excuse me. All right, now what if we wanted to find an inverse? We got f of x, oh, sweet. But I want to know what the inverse of this function is. So let's practice finding that inverse. So first thing we do, we replace that f of x with a y and swap, well here, no, I'll go a little slow. So replace it with a y because it's just easier to work with. And we're going to swap x and y to make a new function. I'm even going to change colors. So this is our new function, and this new function is the inverse function, and it's related to the original, so it has some properties that are kind of carried over from the original. So it's not going to follow all the normal rules, because in order to get it by itself, we got to square both sides, and so we get y equals x squared. So f inverse of x is x squared, which you think is just going to be a quadratic and it's going to have the full u, but it's taken from this square root function. So the information from this is not lost when it moves over to this other one. For this to be a proper inverse, it needs to follow some rules from the original. If we graphed these, so f of x equals, I'm just going to cheat. There's square root of x. I did a 1/2 exponent just to make my life easier. And then our f inverse of x, which I'll just call g of x for now, is x squared. But those are not proper inverses because you'll notice that x squared is not a one-to-one function, meaning that it does not have an inverse. However, square root is a perfectly good one-to-one function, so it does get an inverse. In order to make sure that these two are working together, we need to create a function similar to what we had before, where it ignores this piece of the graph. We shouldn't have that part. You can actually do that on Desmos by doing a little curly bracket and then saying, hey, x has to be greater than 0, and then it will only do that point. So we need to include that in our function. And it's actually greater than or equal to. So the relationship is they're reflected over the line y equals x, the domain and ranges. So for f of x, its domain and range is it goes from 0 to infinity, and the range also goes from 0 to infinity. Oh, those are supposed to be hard brackets, not curved brackets. Hard bracket? Corner bracket? They shouldn't be parentheses, is what I'm trying to say. Same thing is true for the inverse, but it would be these two swapped around. However, they're the same thing, so you don't get to see anything crazy happen. So know that they're swapped, even though they're kind of not swapped, because they're the same. It looks like they didn't swap, but they did. So that would be the domain and range of our inverse, and in green, we have our domain and range of our original function. If you'd like to see another verification of putting functions and functions to verify that they're inverses and finding another inverse, I'll do another one in the PDF notes that you can check out. I'll be doing this one out of Finney book. And I'm going to do this one to determine whether this has an inverse function. I'll do this one in the online notes. So I want to figure out if this function has an inverse. Now, there's a couple ways I can do it. The easiest way is to graph the thing. If not, I would try to solve for y. I would do the swap and make sure nothing funny happened. But the easiest way is to be able to graph it. And we're all about being easy and fast for calculus. So I want to check y equals 3 divided by x minus 2 minus 1. We'll take a look at this function and see if there's any trouble. Now this is a reciprocal function, so it's got that gap in the middle there, but that gap is never going to really meet with itself. It is a hole in the graph, which is fine. It allows it to pass the horizontal line test, and so yes, this one does have an inverse. And that's about it for today. So compositions of functions, that's putting functions in functions, cats on cats on cats. A one-to-one function has each input has one output and each output only has one input. Your inverse functions are just a swap of x and y, which also swaps their domain and ranges. So you need to make sure that anything in the domain and range of the original function is swapped and carried over into the inverse, thinking about like that square root and its squared inverse. And that's about it. This is the last day of functions. Next time we're going to talk about everybody's favorite exponentials and logarithms, making sure we remember all that good stuff. So thanks. Bye-bye.